let's now consider the function f of z equal to 1 over 1 minus z. We are going to find the Taylor series for the case when z0 is equal to 0. So that is the Maclaurin series of this function. Well, we are not going to do all the necessary steps, but you can yourself do it. By differentiating this function, we can find the expression for the derivative and insert this z0 into this expression, and we find the system, and it's a little bit complicated, so we are not going through all the details in this case, but the Taylor series or the Maclaurin series is equal to just this simple expression z in the power of n, and we take the sum from n equal to 0 to infinity, from 0 to infinity. But in this case, we do not have convergence of the Taylor series for all values of z. It's we recall that in the Taylor theorem, the function had to be analytic in the disk with center at z0 and with some radius. And the largest radius we can use in this case is the radius equal to 1. Why is that? Yes, because that we see that 1 minus z is equal to 0 when z is equal to 1. So, of course, this function is not differentiable at z equal to 1 in this point. So the radius of convergence is just this the disk of convergence is just this disk with radius equal to 1 and center at z0 equal to 0. So we have to use this restriction. The absolute value of z must be less than 1. This reminds us of the geometric series, which takes the following form. Maybe you have seen it before. It's the result that you may have seen before is that 1 over 1 minus you use a different variable here, just to not confuse with this set, is equal to the sum from n equal to 0 to infinity of u in the power of n. And of course, in a similar way, the absolute value of u should be less than 1. So how can we use this to find the Taylor expression for other functions? We know that it's difficult to differentiate many times and insert the values of z0 for each derivative. But in many cases where the function in some sense looks like the geometric series or the sum of the geometric series, then we are able to use this formula in order to find the Taylor series. So let's do it for this example. We have now the function f of z is equal to 1 over 1 plus z. In this case, we wanted to find the Taylor series in the case when z0 is equal to 0. That means we are going to find the Maclaurin series for this function. What we are doing then is just to we want this function to look like the sum of the geometric series. So what we are doing now is to replace 1 plus z by 1 minus minus z instead, because if we now replace minus z by u, then we see that we have the limit of the geometric series. So once we have observed this, we know that replacing minus z with u, we have an expression for the this limit in terms of an infinite series. So using this formula for the geometric series, we obtain that this expression is just equal to the sum of minus z in the power of n. So minus z is just minus 1 times z, so we easily obtain this expression, and now we realize that this coefficient is just equal to an, because note that when we are going to find the Taylor expression for any function, we want the expression to look like this. We have sigma from n equal to 0, from 0 to infinity, of an, this is the general expression, multiplied with z minus z0, which in this case was 0 to the power of n. And now we see that this series is on this form, where an is equal to minus 1 to the power of n. So this means that we have found the Maclaurin series for this function. Okay, let's take another example. Consider the function f of z equal to 1 over z. This function is also similar to the sum of a geometric series. Just go back and look at this formula again. We had that 1 over 1 minus u is equal to this infinite series. Now we have 1 over z. So what I want to do here is just replace this 1 over z by something else. I want this expression, and what do I do then? Well, let's just see what we are looking for. We are looking for an expression of this type. We want the sigma an times z minus z0, which in this case the z0 should be equal to 1 to the power of n. So that's what we are looking for. We are looking for such a sequence. If I now replace the function f of z, which I see is in some sense similar to the limit of a geometric series, I can replace it by 1 over 1 plus z minus 1. This is what I need. I want this this expression. Then I see that this is not exactly the geometric sequence, but I wanted a minus here. Recall that the limit of the geometric series was 1 over 1 minus u. In this case I have plus something, but I want minus, so I just put minus here, and when I minus here I must have minus here to cancel this effect. So now I have an expression that is equal to this expression, but I have something here which I can replace by u, and now I have the limit of a geometric series. I know that 1 over 1 minus u is equal to the sum of u in the power of n, to the power of n. And I know that this is equal to the sum. No, this minus 1 is taken outside of the parenthesis, so I obtain that this expression So now I realize that this coefficient is just the coefficient I need in the Taylor expression. So what I have here is just the Taylor series corresponding to Z0 equal to 1. Note that in this case we must have that the absolute value of u is less than 1. It's always the rule for a geometric series. And -1, the absolute value of -1 is just equal to 1, so I can just eliminate this value, this -1, and I obtain that this is exactly the same as saying that the absolute value of z -1 is less than 1. So this series is valid for all z such that z -1 is less than 1. This means that we are in the disk with center at z0 equal to 1 and with radius equal to 1.